Okay, so for showing you all the elements that I want to present to you today, we are going to use Blender. This is a computer graphic course, so it's not outside the scope of this course to at least partially experience with some software, 3D authoring software. Of course, you are not required to know nothing about the software in itself. Okay, well, the powerful technical. No. Okay. Okay.
Ricordiamo solo un attimo.
Ma lo tengo così, non so.
E comunque sto regolando.
Sì, va bene, grazie. Okay, well, easier like this. There are mainly three elements that interact together when we want to compute the final color of a pixel of an image, when we start, of course, from some 3D contents. And the three elements are the observer position, so the eye of the observer as an entry point, sort of, into the scene that we want to render, which is called usually, and is referred to usually as the camera. Of course, in any software you can have more than one camera in the scene. Just one is going to be the one used for the final render at a given time. Then you can, of course, change between the many camera, but in a specific moment, rendering come out from one. The second important element are the light sources. And we will see something about these light sources. Basically, there are two different ways for illuminating a 3D scene. The first one is by using direct lightning sources, and we will see some of them, and also with some indirect lightning method, and we will see also something about that. Last, very important element for defining the color of a point of an image, of a pixel of an image, is the surface, is the object itself that has to be rendered, the geometry of its surface, which is a combination of at least two aspects. The first one are the vertices, so the position, the shape it has into the space, and the second one are the normals. The normals, both to the vertices, both to the faces. So, let's start with the camera. Okay, in Blender the camera is this object that you see here. Is not every authoring tool has its own graphical elements for displaying the camera. And in the sidebar you find some interesting aspect that defines the properties of this object. Okay. 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 On the left side of the screen, you should see just the scene with a camera framing an object, the default cube. You can delete this cube and add some more test mesh, like for example this one. Okay, and in the right side, instead of the screen, you see what you can see through the camera, which is important because all the effects and the features and the parameters that we want to set to the camera are going to affect this part only of the scene. Let's put maybe some other object, for example, a grid. Yeah. Let's make it bigger. Okay, and maybe similar. And cool. Okay, so back to the camera. There are many different parameters that you can set, and some of those parameters we already use it in our coding when defining the view matrix for the scene in JavaScript. You can see, for example, two of the more important, which are the field of view, and can be expressed in degrees or millimeters, and we will see how it may change the view, and the clipping, because you know that a camera is basically a frustum, is a trunk of pyramid that defines what you see and what you don't see of a scene. Everything that is outside this pyramid, this frustum, is clipped, is removed from the final rendering. Everything that falls inside this pyramid is instead rendered. So let's see, for example, what happens if I change the field of view. Of course, on the left side nothing changes. This is what happens when we increase dramatically the degrees of a field of view. So in a way we stretch all the perspective rays, or we relax them very much if we do the opposite thing. The same thing happens in millimeters, where you have this is used mainly to have a sort of comparison when you are creating something and you want a rendering which is close to some camera lens, and so you want to approximate what you can see through that camera lens. Okay. Another aspect which is very important is the clipping, which defines the distances between the closest and the farthest object that falls inside the frustum. Every vertex that falls inside the start and end, clipping the near and the far plane, is going to be considered for rendering. Everything that is outside this range, of course, is clipped. So the effect of clipping is something like this. If I, for example, increase my starting clipping, you see that some part of the scene is simply cut, and you go through the object, which are sliced. And the very same happens if instead I decrease very much the far plane at the point where some of the object disappears from the view. Okay. Sometimes it happens when you import some model that you don't see anything in your scene, and sometimes the reason is that the original scale of the model is so big or so small that it goes outside the boundaries of the clipping planes. So the default are quite right for us. Those two values, those two parameters of the camera, are something that we used, that we have seen in our JavaScript programming. So that's why we are also looking at them here. Camera, of course, can be moved in the space, and that's the results. Camera can be animated, can follow your main character if it is a video game. After all, it's just the final space where everything returns in the end before visualization. The second aspect, which is quite important, is the lighting of a scene. It is important because in the next lessons about WebGL and also the next theoretical lesson, you will have to deal with the light models and the illumination models, rendering equation and stuff like that. So we are going to see something about light sources. Yes, we can continue here. Okay. If I change the visualization way for the scene, now we just have a preview. This is a real-time rendering, but it is just a preview. Every object in the scene is with the same shader technique, the same shading technique. A standard material, we will see materials in a while, is applied to every object, so everything looks more or less the same. It's just for pre-visualization and for helping you in the modeling part of the scene creation. If we go to more advanced shading technique, for example, textures or materials, we see that everything is black. And everything is black because we don't have really a light source in the scene, which is required in order to see something. Lights are just objects, and we're going to see some of them. They are called lamp in Blender, but each authoring tool has its own way for calling them. We are going to see mainly the first three: point, sun, and spot. And we are also going to implement them in our shading codes in the next lesson. Let's start with the point. This is a point light source. A point light source just has one feature, which is the position. It only has a position in the space. Then, from this point into the space, 360 degrees around, light rays are spread, as you can experience. And as you can see here, there's just one point. Okay. Another characteristics they have is the amount and the strength of the light that those light sources can emit. Is called energy here, and if we increase, of course, we can also burn the image in some point. This white is a burning, really. We are going just to 1, 1, 1 in RGB values, so it's total white, which is quite unnatural. And also we can give light some colors, which is added, and this is something that you should remember when creating shaders. Light colors is some to the light, is an addition to the light, to the color of the materials. Okay. A sunlight, on the other hand, is different for another reason, which is, let's go back to a white light, is characterized only by a direction. It really doesn't matter where you position this kind of light source into your scene. it is composed just by parallel rays that goes into one direction. If I rotate this image, you see that light rays start going, surfaces are illuminated according to the direction of this light. A thing that you should notice is that some of the faces of the object are black. We call it normally in real life shadows. They are not really shadows, or this is a phenomenon called self-shadowing, meaning that they are black only because no light source is hitting that point of their surface. It's not really shadows. We will see how to activate real shadows in a while. They require some extra computation, which we are not going to compute in the shading that we will do in GLSL. But normally, since they require extra computation, is an extra effort required for computing the shadows, they are computed only on demand, if you want them. Otherwise, they are not. Also, in this case, you see that if I go completely parallel, okay, you see that I'm illuminating everything from below, even if the position of this light source is over the plane, but it looks illuminated from its below part. This is because we just have a direction. And the third light source that I want to show you is the spotlight. Spotlight is characterized by both. It has a position, but also a direction. Just one step before. If I go to point light and I start rotating, you see that nothing changes because rotation doesn't affect a point light. Instead, the sun rotated really changed, but if I move around in the space, this one, nothing changes again, while if I move a point light, everything changes. So, the spotlight are defined by a position and also rotation. You see that in this case, Blender automatically activates shadowing for this kind of light. As you can see, real shadows are cast by the object on the plane. This kind of light is also characterized by another parameters. You see that it defines only a portion of the space which is affected by its light, which is something completely different from the two light sources before. The other two light sources affected, at least they try to affect, the whole world. One going 360 around the point, the other one with parallel rays that cover the entirety of our scene. In this case, in the case of a spotlight, instead we just have a portion of the space covered by it. Everything outside the cone is, of course, unaffected. As you see, the cylinder is still black. There is just because we are going to also implement this part, there are, just have to check where it is. Spot shape. In this case, we have degrees for defining how much of the scene is affected by this spotlight, and we can also decide the fall-off zone. You see that there are two circles. The outer one defines the area covered by this light source, while the second one defines the area with the maximum intensity. Between the two, there is a gradient of light that decreases as much as you near the outer ring. There is also something that is called volumetric light, but it doesn't. It is not required that you know anything about that. There are also two more light sources, which are the hemispheric light. This light source is pretty similar to, in concept, to the spotlight. The only difference is that it's much bigger. It was originally invented for giving the user, the modeler, the idea of a very wide source, like the sky, source of lighting for a scene, but more complex, more precise method for illuminating the outside were created during the years. So basically this particular light source is not really used. Last is the area light, and the area light is characterized, it should be characterized by not only the direction, which is now completely wrong, but also by its size. The bigger an area light is, imagine this as a sort of a panel. Those used in photography, the white panels that are used just to diffuse lights, to avoid light too strong in a direction, just to diffuse it. And they behave basically like this, like that. Only thing is that you should use, you see them only when rendering. Oh, it's okay, let's try this. Okay. We are not going to see this one because it's useful only when you create complex rendering scenes, not in real time. And since our experiments in WebGL are all about real-time rendering, this one is not useful for us. Let's return to some easy light source, like for example the point light. I just want to show you that light rays must be activated. Okay. And in this case, you see that if we render the scene, right, this light source also projects a thing which is called shadow rays. Each light source has, of course, light rays that are used to illuminate a surface, but lights also can have shadow rays, which behaves on the opposite of a light ray. They allows to create shadows casted by the object on the other objects. The more samples you give to the shadow rays, the longer is usually is the rendering times, but the softer the border, usually the should be more realistic borders of an object you can create. Of course, also increasing the soft size, 0.5. It's taking a while. The soft size means that the border of the shadows are less precise, more blurred. Okay. A nice feature about shadows is that you don't need to make them black. You can change the color and use whatever color you want. Sometimes this is used only if you have to check which light is contributing to which shadows. You have to, for any reason, to recalibrate shadows in your scene. So you want to see which light is the one creating the effect that you want or you don't want. For example, I go for a blue shadows. Render again. Let's go back 30 samples. 5 is more than enough. You see that now the shadows are changed colors. They are blue, which is of course unrealistic, but it has some meaning also. Okay. So up to this point, we have seen two main elements contributing to the final color of the pixel, the camera, and we will see in a few moments why it is important, and then the light sources themselves. They have usually a point into the space, and even if they only have a direction, or even if they have only a position, there is an incidence angle by which a surface is hit by a light ray, and that's what makes, what is really important from our perspective. So it doesn't matter if we only have a point or a directional light, there'll always be a direction of incidence, an angle of incidence, between the light source and the surface. Let's go back to the surface. Okay, let's briefly analyze this object here. If we go into the edit mode, which is the mode in which we can modify the geometry of object in Blender, we can see how this monkey head is composed. And as you may already have guessed, there are vertices. They have a position into the space, and we can move them. At two different vertices connected between them creates an edge, and at least three edges or three vertices define a triangle. In this case, we have a mesh which is composed by quads. Instead of having triangles, as we are going to have because it's simpler in our testing with GLSL, sometimes mesh are encoded using quads instead of triangles. There's a reason, which is usually connected to the texturing. And you will see how textures works in the theoretical part and also in GLSL. So for now, this should be enough. If I select everything and then I ask to show normals, vertex normals for example, you can see those strange spikes protruding from the edge. Those are just the directions where a vertex is looking to. It indicates the orientation of a vertex. The orientation of all the vertices composing a quad or a triangle also determines the direction, usually determines also the direction of the whole face. If I, for example, decide to modify the normals, this should be something like normals, flip normals. Some of them, and then I have to go to something like rendering. Okay. Now you don't see the effect, but usually, I don't know why, really. You should see everything black. But now it's not happening, I don't know why. It really doesn't change it then. Flip, but not really. I don't know why. Okay, normals are really important just because they determine how the surface should behave when hit by a light source. When you import a model and everything is black for no reason because you correctly set up a light for hitting that point in the surface, but everything is black on that particular point of the surface, usually the import procedure failed in recalculating or importing normals. So normals are flipped on the other way, and the engine is considering that phase looking elsewhere. So the light is not computed correctly when bouncing on that particular triangle. Okay. Another thing that, let's call it a trick that can sometimes be useful to know is that you can also make an average of each of the vertex normals and smoothing them by considering also the normal to the face, because each face has a normal, which is the direction of the face, which is derived from the vertex, but you can also change the vertex normal with respect to the normal of a face and then create effects like this, in which there is no hard edge between one face and another one, just because the normals of the vertices were averaged using the normal of a face. And so this creates a more smooth directioning of the normals across the whole surface. The same can be done for many figures. Okay, so those two elements, the camera and the lights, becomes really important when they start interacting with what is called the material, the shader itself used for coloring. Not only coloring, but also for giving some, to approximate some physical aspect of a material. That's why they are called material, and this material is applied to the surface. I think we can have a break, 10 minutes break. Then I show you the materials, and then we can have the weekly test in the final part of this lesson.